Thank you very much, and thank you for the invitation. It's been a great pleasure to be out at SFT. And what I'm going to talk about are some things that I found while at SFT. And I should say first that all of this, what I'm talking about, is not correct with So I'm going to tell some story about large N duality, and I should say also that this is this is work in progress, so not every detail has been proved and so on, but I have been working in and around these things for now a couple of years, and this was always quite mysterious part of the story to me, and now it's less mysterious, so I want to explain where it comes from point of view of technicality. So what is this large N duality? So it's actually some kind of bigger principle, but for us and for today, what it does is relating two holomorphic curve counts. So on one hand, we can count, so we count holomorphic curves, and this is some sort of open Gromov-Witten theory, we should think of being defined. So we have here open Gromov-Witten theory, and it would be some kind of partition function. We'll see more details about this later, but let me write it down. So we will have some kind of the free energy. So we sum overall connected curves, and let's say they have Euler characteristic chi, and then h boundaries, and then we take a genus parameter called gs for string closing constant, weighted by minus the Euler characteristic. So this counts like 1 over gs and more complicated curves with higher powers of gs. But then, what I want to, for this large N, there is another ingredient. So we take the boundaries of these curves. So maybe I should write out what we're counting. So we're looking at maps from the given surface with boundary into star S3, and the boundary going to S3, but technically this magic N here. But the lattice is J holomorphic, as we. That's the idea. Now, there are only constant maps and so on, but let me give you first the flavor of this result. So we take one such surface with h boundary component, and when we look at the surface mapping there, we can just choose which copy of the S3 lands in. So it's in some sense, if we know the curves, it's easy to write this formula. So this is one side of this duality, and the other side is curves inside manifold X, which is twice the O minus 1 over CP1. So this is also a complex free manifold. And in here we count. Maybe I'll call this FS straight. In here we count curves, and now closed curves, so no boundaries. And then B, Euler characteristic, and another variable k. So here we have something like this, and then q to the k. So this q keeps track of, so q, let's say, q is equal to e to the class of CP1. So there's one homology, the second homology class in this space, and we now count the curves, keep track again of the characteristic and their homology class. So just the usual count, and this is the kind of closed logarithm theory, the usual story. And the statement of this large M duality is in fact that these two functions so are equal. So Fs3 is equal to Fx provided Q is equal to E to the N ES. So if you want to think about it from this point of view, you put this into the NGS here, you expand it, and you collect terms, and then this is what you should get. Okay? So that's somehow that's the statement of this large N duality, and one of the main points of it is that indeed it relates some kind of open Gromov-Witten theory to closed Gromov-Witten theory. And now one can do more things here. In particular, one can, and then I will do that, one can include some notes in this story to make it a bit more clearer. So, include some. And then what we are doing is maybe we take a note K inside S3. So why am I doing this? So the problem is that a priori this is a little bit unusually hard count for us because there are no, if you look at this equation, we can all immediately see that there are no non-constant curves here, right? So we have only constant curves, and so it's hard to start from just constant curves and understand what's going on. So I want to throw in a note as well, so we will have some curves. So we include notes, and the way we include notes is as follows. We take, so this is S3, and then in here we have a note, and this note has a co-normal, so maybe I'll call it LK, sits inside this T star S3, and it's the set of all points. Q is some, so you set of all covectors normal to the node, so to say. So it's topologically it's an S1 times R. And if you just look at it sitting there, then it intersects the zero section along the node itself. But in order to have some holomorphic life for this thing, we can shift it off. So I will shift it off by, so it now sort of schematically looks like this. Here this is LK shifted. And how do I shift it? Well, I shift it by looking at the small tubular neighborhood of this K, and inside this small tubular neighborhood, it looks also like S1 times R2. I take the closed one from the theta along the node, and I somehow use that to shift the co-normal. So it's just defined in a tiny little neighborhood. And then we can look at holomorphic curves, you know, inside T star S3, and now we actually have some. We have some basic holomorphic annulus going from LK down to the zero section. It's basically just a curve in T star S1 between graph of the theta and zero section. And then we may again, we can use this duality to say that there is a relation between such curves. You take n copies of the zero section where you allow this boundary to land, and corresponding curves inside the resolved conifold. So this one does not intersect the zero section, and outside the small neighborhood of outside, kind of at infinity, this space looks like the two spaces look the same or asymptotically the same. So we can think of this the Lagrangian conormal as sitting inside X. And counting, and we have the same type of relation between the partition functions.
Yes? So in these open string Gromov-Witten invariants, which ones have a sort of an honest theory with a virtual class that you can define, or are some of them just written down kind of formally here?
No, so I want to tell you what's going into defining this thing. So first I want to just to state the relation and maybe explain what's difficult with this relation. So, yes?
Sorry, so you have GS on both sides and you have this change of variable.
Yes. I will be extremely precise about this change of variables in a while. And just 1 second. I'll try to explain what's difficult. So, what's difficult in proving this thing is that for a long time there was no real definition of this open Gromov-Witten invariant, and I'm going to try to provide such definition. And my definition will work first when n is equal 1, and then I will discuss, how to promote it to n copies of the zero section. And here it's somehow stupidly promoted, and it looks quite stupid, but this thing somewhere goes into some change of variables which connects to what you're saying. So I will try to explain that. So that's one difficulty. And the other difficulty is, of course, that so if you look in the physics literature and you try to look at this proof, there are indeed some proofs, and it's there is a relation using what's called the gauge linear sigma model, interpolating between two theories and so on. This proof is not so much like that proof, at least not, when you look at it, it's slightly different. It would be very interesting to understand all the relations to the arguments that are out there. But I think that part of the problem has been that this side has not really been defined.
Yes?
Yes?
If I set n equals 0, one side looks tautologically 0, but it
Yes.
corresponds to setting q equals 1, which makes the other side not look tautologically 0.
Right.
Wait, what about h equals 0?
I mean, but I mean, is that what's happening? That
That's in a sense we are forcing h to go to 0. That's right. H is 0 in the end, but it's too naive to say that this n to the h is just 1.
but the left side does include somehow the contributions of closed curves.
The left side, exactly. So in this definition of the open Gromov-Witten theory, we'll see that it's impossible to define the open Gromov-Witten invariant without counting somehow closed curves with something in them. So that's indeed the case, and that will be the proof. So the proof that we will carry out is we will find out what's the contribution of the closed curves, and somehow find a deformation makes everybody a closed curve, and then we're basically over here. So that's the main idea. Okay. So let me try to. I should say one more thing. So before going into detail, I would also like to connect this up with some parts of physics that maybe is obvious to anybody who studied the subject kind of carefully from the beginning, but to me it was not obvious until not so long ago. So there is one further. So why is this interesting? One could ask, but there is one further piece of information that's needed and what was used over many years very successfully. So that's somehow Witten's relation. Between this open Witten and T star S3 and Chern-Simons gauge theory. So, to say something very fast again, so basically there is a Chern-Simons theory which integrates maybe we want to know this Chern-Simons action. So it takes so A is a UN connection on the trivial boundary S3, and this Chern-Simons function is basically ABA plus 2/3 A wedge, A wedge, A. Something like that. And then here you're supposed to do a path integral. Then you integrate over all such gauge equivalence pairs of connection, you get some kind of invariant of the free manifold. And that has a partition function, and that partition function is supposed to be equal to the exponentiated version of that function. But that's not the first thing I want to talk about. I want to talk about, again, that story with nodes. Should say what was the change of variables. I'm not going to use this super much, so let me not go into detail. But to relate the two, we should have GS be 2 pi I over K plus N. So N is the rank of the gauge group, and K is this level of Chern-Simons, so that's what gives you the variables here. Now, what one can do in this theory is you can take expectation values of nodes. So given this path integral, and if you have a node in your three manifold, then you can take the holonomy of this connection along the node K, you take the trace, and you integrate that. So that's a kind of some expectation value of the node, and this is famously the Humphrey polynomial in two variables, e to the gs and e to the ngs. Maybe there are halves here or something like that. It's sometimes q, and this is q. Maybe to 1/2. Okay. So that story will enter here. We will kind of come back to showing something like this in some sense. But there is one point that I want to make, and that's the following: that if you look at this open Gromov-Witten theory from point of view of physics, there is a different viewpoint on this insertion. So here what we're saying is we take the knot, this is called Wilson line or Wilson insertion. And then there is a double point of view which is called Toft insertion. And instead, then, so what Toft's idea is, there's kind of some big industry around this, but in this example, what does it mean? It means that rather than inserting the knot and integrating along it, we can insert a singularity in the connections along the knot K, and use that to do the path integral. So basically, you see, and the singularity is such that that the monodromy of a knot, when you kind of a little guy that goes around here, where basically it's a concentration of curvature along the knot, right? And so from one point of view, so I was always a little bit confused about that. So when you do this open Gromov-Witten theory, then there is a kind of a question as to what. So you write up some path integral that localizes on the space of holomorphic curves with boundary, and then you should do an integral over there to compute the partition function. Now, that integral is taken over a space with boundary, and so from Gauss-Bonnet theorem, one would not expect that you integrate the form over a space with boundary and get something unequal. So there should be some boundary term. And the question is, what is that boundary term? And I will try to explain how one could think about it. But I think better from point of view of physics, there is another point of view on this, which is the following: that you should think in this Witten spirit, you should think about Chern-Simons theory on S3. And then you have some holomorphic curves landing there. And then you should think about these holomorphic curves as deforming that theory. And the deformation, the curvature inserted on the knot itself, is proportional to the area of the holomorphic curve coming there, and with the genus parameters. So we can somehow view these holomorphic curves not as being counted, but rather by giving kind of deformations of this this Chern-Simons theory on the three-manifold, and what we're saying, the deformation is such that the curvature is, you know, for a little loop going around is exactly, maybe if I do U1, it will be proportional to the area of this curve. And note that from this point of view, what I'm going to explain what we have to count, and I will try to reconnect to this picture. So let me now go to what we should count. So,
Tobias, are you expecting to get an identity between the Wilson line calculation and the top line calculation, or are they written with some non-trivial duality?
from here, I think it's just identical. You can either do one or the other. Yeah. Okay, so let's see. So let's look at one. So look at first at n equals 1. Okay? And we would like, and maybe let's take this case when we actually have some curves. It's difficult. I will come back to the S3 case, but it's easier to think about this case. So we have some curve sitting between the LK and the S3 boundary. And now I want to change the almost complex structure. So how to make open room with a potential invariant. So that's the question. And okay, so imagine that we can achieve transversality for these curves. Maybe in this case, if we count those ones around this thing, it's pretty easy. And now we start changing the almost complex structure. So we must indeed look at, you know, what can actually happen in one-parameter families. And in one-parameter family, there are somehow, so in one-parameter family, of almost complex structures, or if you're in a more fancy situation, and you don't, I mean, if you count things that go 5 times around, then you wouldn't get transversality without some extra perturbation, but when you know, so you should think about deforming the whole perturbation data in one parameter family. The following happens. And this is the usual story, and of course nothing else and so on. So here I'm drawing a boundary of holomorphic curve. So this is boundary of holomorphic curve, and this is boundary of holomorphic curve. So for generic time parameter, the boundary of the holomorphic curve is a knot in the three-manifold. When you vary, at some points it can self-intersect, or you know, two pieces would come in and intersect. So that's one of the things that can happen. And the other thing, so maybe, yeah. So let's look at this. Let's look at this picture. So. Well, maybe I'll list with the other one as well. So how to find the other one? So you can, if you think in 2 dimensions, you know, from one side, maybe I'll draw the resolutions of this thing. So on the one hand, we can view it as a kind of just two pieces of curve going straight through. But as they cross, there is another. There is also some other branch of moduli space ending there, which is obtained by smoothing the curve. So I'm going to draw it like this. And to understand this thing, we should look at deformations of, you know, in the plane, just x, y equals epsilon. So for epsilon, so you know, so what I'm trying to say is just something very basic, that if you want to understand this family of curves, you can take this is the branch of x, y is equal epsilon, and then you come to the cross, and well, just you know, for x, so the 2 lines are x, y equals 0, and this is xy equals epsilon. So this is some kind of very familiar picture. Now, when you see this equation, you should expect to find a kind of elliptic analog, and indeed that's the second problem, which I would just draw like this. So here is the singularity, and what comes out is maybe first empty, something like that, and then there is a little circle born. So this is like x squared plus y squared is equal epsilon. So for epsilon less than 0, we have no solutions real, and then for epsilon bigger than 0, we have a circle of solutions, and something is happening out there. So let's somehow look at this a little bit and see what really is the problem. So imagine that you have in the whole, that's not going to be realistic, but imagine that you have just two holomorphic disks forming on this Lagrange. You want to count these. So then, for some almost complex structure, they maybe look like this. And then you start deforming, and at some critical instance, they intersect in one point, and after that, they're free. But what happened was that there was a third disk that somehow looks like the other two, and it was created here. So on this side, if we count naively, we count 2, and on this side, we count 3. So that's not so great for invariance. But what we can do is we can somehow save the day by counting with obstruction chains in sort of the spirit of Foucault. So, or bounding chains. So one possibility of curing this in S3 is that we pick, we count with linking numbers. So we pick a bounding chain for each one of the disks. So we pick one here. In S3 there certainly exists such a thing. And then we count basically linking numbers. So, and you see that on this side, what I want to say is we should count this graph of disks, and then we should count another graph of disks, which corresponds to these two with, yes?
Also, no, your circles and blue things are all in S.
All in S3, yeah, so yeah, everybody is in S3. So circles are boundary to holomorphic disks. Boundaries in S3, and I pick a cap for each one of them, and then I can count intersections with the white and the blue, which is some kind of linking number. And so what I want to say is I count, this disk, that disk, and I also count the configuration, which is these two disks and, maybe a pair of points, or one point in the intersection of the blue and the white. So I find now 3 disks on this side. On that side, I would find no linking, and I find 3 dots, right? So, and then so somehow this formal, this what I call generalized holomorphic disk, plays the role of this holomorphic disk. So if I do this, the disk count will survive. So this is in the spirit of kind of Floer theory and whatever infinity structure, something like this, if you try to do it many times.
Is this discussion sort of limited to genus 0, or you can do higher genus with the same?
I'm now going to do higher genus, yes.
I think in this case, Velchanger had a proposal like that a while ago.
Yeah, I think so. And there is also this Jacobino person who did this long time ago for disks and so on. So this is not maybe a new idea, but let me also say one thing to connect back to this kind of Toftin circle. So now if I deform the connection along both these things, then this circle will know this deformation, and the other one is knowing this deformation. So in some sense, if I write this blue bounding cochain is a way of picking a potential. So if I want to have something with curvature here, and I have this blue kind of gadget, I could define something which is basically heavy side. So if I take some x, I don't know, y, z. So I can take heavy side in z times Dirac in y dy. So that's my kind of connection supported along here. When I take d of it, I get the prescribed curvature. So in some sense, this is a like geometric realization of picking a Toft potential that allows me to induce the right deformation. Okay. Now, what happens at higher genus? So at higher genus, unlike with the disk, so if in the case of a disk, if you have, what's the simplest thing? So the simplest thing is that you have, the same disk intersecting this disk at 2 points, right? There's bounding chain at 2 points. So if you're doing disks, then you cannot glue first here to this disk and then here because you go to high genus. But in high genus you have to glue everywhere. And what the claim is that in high genus you should just do the same thing, but instead of counting just these guys, you should count all kinds of graphs that you can dream of. So rather the contribution from here would be, so the edge should be weighted by e to the gs rather than just gs. So that's a nice thing. Now, or if you want to be precise, so here if you want to count linking number and you count them like crossings, then each crossing counts 1/2. And if I put these dots in here, then I should take e to the gs over 2, right? So somehow each crossing counts half a linking, and so I put gs over 2. Okay, so that's one of the things that can happen. But once you see this, you need to think about another thing that can happen. So when I have maybe I'll do the following. So in S3, I want to create these blue things in some concrete manner. So I take a gradient. I take a Morse function with two critical points, and I take the gradient flow starting at this one to give my blue chain. So here you can think of it as going out to black 4. So that's the usual kind of link diagram I get, and I count the crossings, right? So that's how I create my blue things. But then there is one further, once I say that I create my chains like that, and I follow them like this with an almost complex structure, then it looks pretty good up until this point happens. So I can have the following disaster for my scheme. So here I have some kind of, to get the orientation right, but I never get it right. So what is this picture indicating? It's indicating that, here I have a curve with a kink. So it's a kind of a self-linking, which I haven't really defined, but there will definitely be intersections between the bounding cochain of it with itself here. And so I count this curve with this weight, full genus potential. And then what happens is that this looks singular, but it's only singular in projection, so it's coming up. Maybe I should write the equation. So I'm looking at this family of monomorphic curve, where t is the parameter along the curve. And here I take C first to be, so here C is negative, and here C is positive. So what's happening is that here, here you have two solutions when C is negative, which is this double point. And then when C goes to 0, that double point goes away, and here there is no solution. But, and so it looks horribly bad, but there is a kind of saving grace, and the saving grace is a 4-chain. So what we need to do is to take a 4-chain, in this case, we can take the boundary of the chain C, the boundary of C, and I will take it to have boundary 2S3. And if you wish, in this simple case, we can take this C to be just R times the gradient of F. Okay, so So basically, you take this gradient of f, it's a, or yeah, dual. So gradient of f we can think of as a field of one forms, if you wish. And now we shoot out, maybe I should not say that, I should say this. We shoot out the ray in this direction, so we get the 4 chain with boundary at infinity, which I'm not going to care about. And then it has boundary on the 0 section S3. We take the same chain, but with opposite orientation going in the negative direction. And now if you look at this thing, so in this case our chain will go off, you have a 4 chain in the fourth direction. So if I look at this curve for C bigger than 0, then I could ask, where does so we have a 4 chain and we have a 2-dimensional holomorphic curve. So where does the holomorphic curve in the interior intersect the 4 chain? And you see that as this guy disappears, there is a 4 chain appearing here, right? So what does it mean? Well, we need this guy to be real. So if you think about the curve as parameterized by, this is sort of the t-plane, upper half plane, then this one has to be real to intersect our 4 chain is 3 real coordinates and the imaginary coordinate in the c direction. So this one has to be real, so that means we're either on this axis or this axis. And if we're on this axis, this one is purely imaginary, this one is real, right? So this one better be 0. And it's 0 exactly at t is equal to plus or minus square root of, I times c. But in our curve, there is only one such point. The other one is not in the domain. So it's like that. And you see that here, when you plug in, it really intersects the 4 chain, right? So there is a way of counting these things. So you take your curve, you have to shift your boundary off of the 0 section, and then you count intersections with the 4 chain, and each such intersection should also count like that, right? So you have the 4 chain, you look at the interior of the curve, you see where it intersects, and you treat those exactly as these boundary chain intersections. And then we survive this disaster. So now we need to look at this seriously at each and every genus. So let's see if we can retain invariance. Let's see what happens for the crossing. And then, so we see this curve, it's somehow coming in with the crossing, it crosses and it goes through and some sort of new. So when I look at this one parameter family, I have a coordinate starting here with the overcrossing, ending here with the undercrossing, so we should somehow expect to have some kind of relation like this. And then we should look at all the curves that appear in this glue. And we found one of them. So this was the sort of standard curve, the xy is equal epsilon, and so on. But now we need to understand this not just at this level of GS, but we need to go further. And so what I want to claim is that when we come very close, then there are contributions from all these constant curves living in the 0 section. And I want to tell you how to treat them. So let me first reformulate this basic gluing in terms of more symplectic geometric gluing data. So what does it look like? So what we have is we have these two curves approaching, and when they're far away, then somehow these constant disks do not interfere much with them, and we don't have to care. But when they start coming close, then we have to see the input of these constant disks. So we take a little constant disk, and I'm drawing the boundary of this constant disk, kind of perturb. Constant disk. And the problem with this constant disk is that it moves in the 3-parameter family. It should be rigid. But if I mark, so maybe I present this constant disk as actually a round circle, then I interpolate somehow this interior. And I pick the two mark points which are the top and bottom values in the z direction, and one other mark point where the boundary is tangent to some reference vector field, something like that. Let me not detail it, and I should admittedly say that I haven't really written this down with any detail, but it's something like this. Okay. Now, now this space with 3 mark points is as big as it should be. With 3 mark points, the constant this should have a 3-dimensional evaluation map. So we have 2 points. Let's call it infinity and minus infinity. And we can take the evaluation at infinity times the evaluation at minus infinity. And this sits inside S3 times S3. So this is some 3-dimensional manifold in S3 times S3. Now there is another 3-dimensional manifold. So let's call this one branch 1 and this one branch 2. So we have evaluation along branch 1 times evaluation along branch 2. And this also sits in S3 times S3. And the gluing happens when these two intersect, and for generic choice of these little disks and so on, they will be transversed, and I glue them, and somehow that gluing should of course be exactly like the usual glue. That's just a slightly strange way of doing the usual gluing, and maybe it won't look exactly like this, but slightly different, but that's how it should work. Now, once you've seen this gluing prescription, you see there is nothing that stops me from using many such disks. I could use one disk, I have one such problem, I take an intersection, I glue. I could use 2 disks, and the other family would also intersect here, or 3 disks, or 4 disks, or 5 disks, or whatever many disks. And each kind of time I glue, I have the same problem, the same intersection point. So what we learn is that there should be contributions, not just from this guy, but it should actually look like this, right? And so on. Many little dots. Okay. So now let me try to argue that, in fact, if I look at this constant, and I should emphasize that what I'm talking about now is something that needs to be proved. I haven't, but I believe that's true. And I believe it's somehow not infinite work to prove it, but finite work in concrete and some other things. Okay, so imagine what we could do more. We could insert here at this point, in some sense, we could insert any constant holomorphic curves. There are lots of them, right? But what I would like to say is that if you try to do that, you would meet some kind of problem where you have an obstruction bounded over the space of such curves. And the successful gluing should be the zeros of this section. But this is a space width boundary. And you can take zeros of such a section and push them to the boundary. So what will happen with the complicated curve at the boundary is that it breaks into some simpler curve, and you'd have some kind of compatible sections here which would give you the gluing. As you push all the zeros off to the boundary, you come to a new problem on the boundary with obstruction boundary. You push and you push and you push, and somehow you can push all the contributions until they're only disks, until it's maximally broken. And what I'm claiming is that my count here is somehow counting at the general contribution, but I'm counting it at the maximally broken curves. Okay, so when I come from this side, what I try to convince you is that I have, rather than this picture, simple, I have this picture. Two squared here. And so on. So that's what happens when I come from this side. Now from this side, I have to use the other bounding cochain. So I have another similar, exactly the same gluing problem, in fact. And the only thing that differs is the crossing sign and the direction of the moduli space. So here I'm approaching from this side, and here I'm approaching from that side. And what it comes down to is that, in fact, you get the same thing with minus here and plus here, minus here, plus here, and so on. So at the end of the day, if I count these things up, what I would find is something like, what I find is something like GS plus GS cubed 2 squared 3 factorial and GS 5 2 to the 4 5 factorial and so on. So in some sense this would be, if you just count the curves, it looks like e to the GS half minus e to the minus GS half times this. So that's one of the cases. And then the other case is when I have this elliptic, when I have this other disaster that's now gone. So remember there was this, what does it now look like? So here is the zero section, here is a curve, and it intersects the 4 chain as a plus. It can go through, sort of schematically it goes through and it lies on the other side, it has minus, but it can also split into some kind of thing like this. Right? Again, I can view this gluing as the following type of gluing, that I'm actually attaching rather a little constant disk at this point. Rather than sort of going down, opening up, I glue a constant disk at this point. And when I do so, I get exactly the same kind of gluing problem. So on one hand, I have to glue the constant disk from here, and I mean it's hard to draw this picture correctly because it's still in dimension, but here there's a minus, and so I should glue them at the other side, and the count is kind of exactly the same. So what we would find out is something like this. That's a GS perhaps, and then. So what this says is the sense that for one brane, if I count curves, just as I was explaining by taking this linking contribution and inserting this factor for each linking contribution and inserting the same factor for each 4-chain intersection, then in fact my potential survives the deformation. And now, exactly as Ivan was pointing out, you know that there could be some closed curve which has no boundary, which intersects the 4-chain only. And the contribution from such a closed curve, let's say I have a sphere, and it intersects the 4-chain, then the contribution from that is like, you know, formally opening it up like this, so you have to count it with e to the GS. Yeah, so, now, I think maybe let's do first the baby version of this without the n, and then I'll explain with the n. So, let's see how we could prove something like this large n now. So let's maybe stay with the not case. So we have a curve. There is this one more trick to the story. I want to tell you. This is k. This is f. We take those curves that goes once around, and now I want to use the fact that I have an invariant, almost complex structure, and I want to choose a specific family of such structure. So what I do is I fix, so this is some distance delta away, and I fix some kind of epsilon here, which is much smaller than delta. And now, if I look at the epsilon sphericized cotangent bundle of S3, that's a contact 5 manifold. And it's a convex hypersurface inside T star S3, it's the basic one. So what I want to do, here's S3, and here's this contact hypersurface, and what I want to do is I want to SFT stretch the almost complex structure here. So this is a procedure which you can imagine making this neck very, 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 very long. Right? And so I want to stretch here. And when I SFT stretch, there is a counterpart of Gromov compactness to the Ashford, Bourgeois, and Wozensky Sender, that tells you that under SFT stretching, holomorphic curves converges to buildings of holomorphic curves joined at the orbits. So in our case, pictorially, we start out here on LK, and then we go into this epsilon boundary, and inside this epsilon boundary sits some kind of other holomorphic curves that joins these two closed curves, right? And this is really the key point to this SFT stretching argument, that the dimension here, the dimension of these curves, is the sum of indices of these ray orbits. So in this case, because we're working on S3 has this round metric, where there is no geodesic which has index less than 2, so that means that the minimal dimension is equal to 2 in here. And you know, then the outside would have to be dimension minus 2, because our curves are 0 dimensional. In Calabi-Yamaha case. And that's not generic, so basically what it means is that when I've stretched, then everybody is outside of the 0 section. All the curves have to go to some curves outside of this epsilon neighborhood. So, for stretching close to infinity, all curves outside S3. So I can write up a generating function for these curves as follows. So I can write my generating family CK chi gs to the minus chi, and then I can keep track of the, so this is the homology class of fiber in sphere fiber in T star S3 minus S3. So because this is now where my curves live. Right? So nobody lives inside the, nobody touches the S3 anymore. Everybody's outside. And so I can write up such a potential. But if I know this potential, then I know the open Bromo-Witten potential as well, right? Because now nobody has anything on the 0 section. I just have to count this thing in the 4 chain. So the open potential set U is equal to e to the gs f, depending on how you know it. So we have this potential that recovers the open one, and it's counting some kind of holomorphic curve stretching from this LK and not touching the 0 section. And now the last piece of information, of course, is large n, is the following: that if I take these curves, so what do they look like? I have a strange, almost complex structure. They have left the 0 section. But outside the 0 section, the manifold T star S3 and the manifold X looks basically the same, provided I take this area of the CP1 to be very, very small. So if I take it very tiny, the curves that I just counted are exactly the curves in X. And that's somehow is the large n. Right? That's transforming the open string count to closed string count. So in the last 2 minutes, let me just comment on what it would give. What's the n and what's going on when I don't have a co-normal. First, if I don't have a co-normal, I would have to start my story from the zero section itself. Right? So I have no curves. But what I'm claiming is that what's important for this argument is that I find an abstract perturbation scheme for which my curves are actually holomorphic inside some epsilon neighborhood, and then they do whatever they want. They're kind of solving this equation for some right-hand side v. And I want to take this v so that, given below some genus or something, everybody is holomorphic, honestly holomorphic inside epsilon neighborhood. Then I can stretch over epsilon to the 1000 or something like that. I stretch all the boundaries away. I get closed curves, which I can then find also in the coniform. So that's the story of closed curves. And then what we really want to do is we want to relate this to n branes on S3. So now that story is a kind of souped up version of this relation. So remember what I did. So I'm now going back to here in the last 1 minute. So what I did here was somehow I looked at the crossing when it happened in one brane. So now I need to remember that I have n branes, and not just one brane. Let me draw the picture over here. So rather than crossing through one brane, I now have to remember that this is happening many times. And basically you can get a picture where it somehow first happened in the first brane, and you go and it happens in the next brane and in the next brane. And then you need to count these things up. And what happens is that for each such, linking and forechain in the brane, you introduce a variable v. And what happens is that you get this equation. And it's a funny calculation that I hope to do, but unfortunately I have to do it in the break for those interested. So what is this? So somehow So what happens is that this is basically counting, you get stuck in the first brane, all the other branes are positive linking. You get stuck in the second brane, one is negative linking, all the rest are positive, and so on. And then you have to sum up these little things. But now we're supposed to do this in this sort of with n branes. So we work, rather than here, we work in the skein module or something like that. So we want to replace every little circle with its expectation value. This can be made precise in the skein module of the three manifold, or if you think in terms of Chern Simons. So what you find is basically this thing should be replaced in that case by the following funny equation. So you should have e to the gs expectation of the circle and just keep this as insertion in scale mode. And so what you see when you sum this thing up, you find that this is exactly equal to v to the n minus v to the minus n over v minus v minus 1. And this is none other in the right variables than that guy. So basically you have to put v equal to that thing. And then the skein relation holds for the boundaries of the holomorphic curves, and you get the large n duality. So somehow in answer to Melissa's question, the actual change of variables is something like this. Q is equal to e to the mgs expectation value of the unknown. So there's kind of there's more free variables than you would think. This is the expectation value of the unknown with gs and with this 4 change. And they're related like this. So I'm happy to try to detail this to anybody, but it's interesting, and I think this is really for kind of symplectic people, so that this is kind of the name formulated in a very kind of eloquent way. So what would happen? So what's telling me that I have to use the unknown here? What happens if I try to import trefoil? So if I try to import trefoil consistently, well, if I try to use different knots in different brains, then I go crazy probably. But if I use the trefoil everywhere, then I would probably be forced in my perturbation scheme to somehow undo the trefoil before I can connect to this big. There is an actual knot, right, which is a solution of the actual D-bar equation. So there would be some kind of wool crossing going out of there and so on. So it's there are many things like that that I don't know the answer to. But what the final remark is that in these perturbation schemes that we study for homomorphic curves, in this three-dimensional case, they're supposed to know a little bit more than just maybe what we sometimes detect. They're supposed to know maybe not the knot exactly, but the knot inside the skein. So somehow the collection of these. So that's the lesson. Okay, thanks. I'm sorry.
Are there any questions or comments?
Luis,
Yes.
I missed a bit how do you started with like a count with curves with bomb around S3, then you kind of stretched, and how did you get to the closed curves? Because on the other case where you can shift off the LK, you understood that you can push everything into the conifold, all of this.
Yeah, so when I don't have a node, what I'm saying is that I have to pick my perturbation scheme, or you give me any perturbation scheme from anywhere, and then I deform it so that when I write up my actual perturbed curves, then it solves an equation like this, right? So what I'm requiring is that this right-hand side should be 0 inside some tiny neighborhood of the 0 section. So inside some epsilon neighborhood, these curves are somehow honestly homomorphic. It means I just take a real analytic circle, I multiply by I go out, and then outside I do some funny stuff. But if I have such a perturbation scheme, then I can stretch within half of this neighborhood. And the stretching is just a normal one. And the boundaries leave. And what I'm left with is some closed curves. Right? So this one would have to go into some kind of sphere or something.
Why did the boundary leave? So it's still stuck to the 0 section, no? Or
No. I stretch along the S3. So if you want to be still stuck to the 0 section, you have to count the
you're
math.
just moving to the kind of like the upper part of
No, upper curve. Let's assume that you have this type of curve, right? So you can have anything outside, and then you want to have something like this inside.
Yes.
So what is this? So this is a wave orbit of S3, and it has index at least 2. And dimension of this guy is inside therefore at least 2. And this one is minus 2. Cannot help.
Okay, so. But you had something that you start. So you're saying that everything kind of like bubbles off.
Yeah, bubbles out of the 0 section. Yeah. Somehow it has to move out. Yes.
So the argument seems to need that you start with an integral homology sphere in which all wave orbits have index at least 2.
Yes, exactly. Yes.
Are there any others?
I think there's some kind of maybe famous theorem of Perlman that tells you something is going on if you don't have S3. So there is a kind of a story which I should tell. So this is a kind of excellent question. So what happens if I count curves? So let's take let's take T star M where this is not S3. So what would happen? I can try to run my argument. I take my little curves and I stretch away. So now kind of Renato's protests are valid. Because now there will be geodesics of index 0. So now I cannot pull everybody off of the 0 section. And what I'm suggesting is to keep the stuff in here. So in that case, the Gromov-Witten invariant would be take values in something like the skein of M, which keeps track of the boundary tensor, basically ray orbits, and some kind of algebra of ray orbits. But so the truth of this story is that here there would be, this is some kind of the actual place, the right hand, the whatever side that attends with is some kernel of some SFT operator, counting some, counting whatever would be up here. One-dimensional curves and the boundary. So this is not completely true as stated. And what I'm suggesting is that is in fact the open Gromov-Witten invariant of that manifold. That's what you have to plug in whenever these manifolds sit anywhere. And this is some kind of question as to what happens, with regard to Witten argument, and there's not only the trivial connection, but the connections can have monodromy here, and that's probably what's going on. But I don't know where this SFT equation shows up on the gauge theory side. Maybe it does, maybe it doesn't. I don't know. But that's indeed true, and you have to, yeah. But also, so for manifolds like S1 times R2 that are abundant in this thing, there's a sort of one calculation you have to do. So you have to find these. You take the orbits going around the one geodesic, perhaps to stretch to that. You have to find out exactly which knots there are, and you can do it by similar tricks, but that's so. Yes.
Okay, so I thought there would be a third side to the open topological string, closed topological string, and then, like you said, string assignments. And if there'd be some kind of Hanfly polynomial or something that should also be equal to these guys, maybe after normalizing.
Yeah. So
did you prove that now? Was that already known? How does that fit in?
Yeah. So what about the whole? So now after this souped up version, we know that the boundaries satisfy this skein relation.
Right.
So now if I take the curve that goes once around this guy, and I go down to the 0 section, it's not hard to show that at outset, if I take the distance to be small, there is one such curve. There is the cylinder going around. And so what will it contribute in the skein? So there is some kind of framing, which is called right, if you think of knot diagram. And then times k itself, right? And just knot itself. So I take this thing, and now I stretch. I stretch, I stretch, I stretch, I stretch. And eventually there is nothing left there, right? So what I'm left with is I'm left with a Hanfly polynomial in variables v to the n and v times 1 and times this factor. So that proves that this counter curves is the Hanfly, and if you go over to the conifold, it's still the Hanfly with the right change there. And so then the normal thing is about the colored Hanfly when you go many times around, and that's you can tweak it out of this story, but it's some additional work. So I think, and that's maybe, yeah. So I think maybe the moral story is that whatever you do, what you need to understand is basically these things for M branes. And once you understand that, you use SFT stretching and you get as much as you can out of this. And that will prove the duality, will tell you better what's going on than somehow what's something.
Okay, let's thank Tobias again.